So I thought it might be a useful idea to do the solutions to the homework question, as a video, so that maybe you can follow what I did and how I solved those questions. Okay. Anyway, so let's start here. Question 5. It's a typical type of question that we would see as question 12 in the Leaving Cert. So for part A, we have to answer all the following. So the first question is to define moment of force, and you can see that I wrote a definition as it should go in. Moment of a force is defined as force multiplied by perpendicular distance to the fulcrum, and it is a vector quantity, and unit of moment is 1 Newton meter. So moment is force times distance, and its unit is 1 Newton meter. The second part of this question is asking us why a crowbar is often used to pry sealed containers. So this is an image of a crowbar. Take a look at this. We would use this part of the crowbar to open up door or a sealed container, and that part would probably be wedged from here. One second, sorry, let me just get a pen in here. So from here up to here, that would be wedged in the door, and we would be exerting force between here and here. So what it means is that exerting a much smaller force over here, pushing it downwards, we could exert much higher force going upwards over here. That's just a principle of operation of a lever. So, and a good answer to this question would be that a crowbar is a lever, and it can allow us using a small force at one end and exerting large force on the other end of that particular lever. So then we'll move on to the next question. Okay, so for the next part of our problem, we're looking at suspended ruler. It's suspended by a thread at 20 centimeters mark. There is a weight of 5 newtons placed at 8 centimeter mark, and the weight of the ruler acts through 50 centimeter mark. This problem is asking us to find the weight of the ruler. So the first thing to note is that the ruler is in equilibrium, which means that the moments and forces acting on that ruler are all equal. So counterclockwise moments are equal to clockwise moments, and forces acting upwards are equal to forces acting down. Now, we're going to look at moments in this case. So moment is obviously force times distance. It's important to note that distance from the suspension point is not exactly the same as the reading from the mark. So we know that 5 newtons is suspended at 8 centimeters. So that distance d1 is equal to 12, and in meters that will be 0.12. We also know that distance d2 between the suspension point and the point where the weight acts at the ruler is equal to 30 centimeters. So that will be 0.3. Now I know that ruler is in equilibrium, so both moments are equal, both counterclockwise and clockwise. This is the counterclockwise moment. I called it m1, so that's 5 times 0.12, and this is my clockwise moment, m2, weight times 0.3. Obviously, I rewrote it as m1 equal to m2 because we know that the ruler is in equilibrium. We substitute the two values into our equation. 5 times 0.12 is equal to weight times 0.13. Simplify and find weight out of this equation, and we end up with weight of the ruler being equal to 2 newtons. For the next part of this question, we are looking at a slightly different situation where the ruler is suspended at 30 centimeters. And the question is asking us to find distance where the weight of 5 newtons needs to be hung so that the ruler remains in balance. Okay, so I noted that I'm looking for distance d1, which is distance between the force of 5 newtons and the suspension point. d2, we know that's the distance between where the weight of the ruler is applied to the ruler. So that distance will be 50 centimeters minus 30 centimeters. That's 20, and it's in meters, 0.2. So now in equilibrium, counterclockwise and clockwise moments are equal. So for the counterclockwise moment, we have 5 newtons times distance d1, distance which we're looking for, and that's equal to 2 newtons, the weight, times distance 0.2. We can find the d1 from that equation. D1 will be equal to 0.4 divided by 5, and that's equal to 0.08 meters. And we need to, if we want to express this in where the weight will be hanging on the ruler from, so we can say that 5 newtons will be hanging at 30, the suspension point, minus the distance. So it will be hanging at 22 centimeter mark. Question is a definition question. So what is a couple? And simply, couple is a pair of forces of equal magnitudes. They're acting in opposite directions. And that's it. They're applied at different points of a circle. So for instance, a force couple would be something in those lines. If we have a rotating circle, we have force acting upwards, force acting downwards. Both of those forces are equal in magnitude, but they're acting in those opposite directions. Also, their line of actions do not coincide. So that's a line of action of a force. This force acting along this line, this force is acting along this line, so they do not coincide, which results in torque being formed along this from those two forces. And torque is simply the moment of two forces, and torque is defined as magnitude of those forces, so F, and if we call that distance d times d, and the common symbol for torque is small Greek letter tau. So torque is force times distance between two forces in a couple. And the next part of the question is asking us to calculate the torque of two forces that are acting on a jar. The thing to recognize in here is that the radius of a jar is only half of the distance between the two forces. So the radius of a jar is 0.03, so 2 times 0.03 is equal to 0.06, and if we multiply force times the distance between the two forces, we'll get the result of a torque for this particular situation to be equal to 0.72 Newton meters. Next question, we're looking at a knot that needs to be tightened to torque of 60 Newton meters. What size force needs to be applied at the end of a spanner given the dimensions are as shown? Take a look at the figure. In the figure, we have a dimension between the head of the knot to the knot and the end of the head of the spanner of 4 centimeters. The total length of the spanner is 20. So we're tightening that knot to a torque of 60 Newton meters, and that torque is the same as the moment that's exerted by the force pushing down. The torque and the moment are a little bit confusing in this case because of the couple of the forces, as you know, torque being the moment of the couple of forces, and we have torque in here and just the moment of a single force. But in general, the base thing to note in here is that the value of 60 Newton meters is the value of rotating a moment that's caused by force acting at the end of the spanner, which is this force. So that 60 Newton meters will be caused by this force acting at a distance of 20 centimeters. So we know that the force is equal to, that 60 Newton meters, that value will be equal to force times the distance. So the force is simply 60 divided distance of 20 centimeters in meters, 0.02, 300 newtons. So that's the answer to the first part of the question. The second part of the question is how much less force would be required if a tube of length 96 centimeters was slid over the spanner. Take a look at this. If we slide that tube over the spanner, the bottom end of the tube will stop at the head of the spanner, which is 4 centimeters away from the knot from our drawing. So the total distance from the knot all the way down to the end where we're applying our force F, that the distance will be equal to 96 plus 400 centimeters. So that's what I noticed over here. And now we can simply apply the same formula where force will be equal to our moment of 60 Newton meters and divided by the distance of 100 centimeters, which is 1 meter. and that force will be equal to 60 newtons. The question is how much less force would we require? So I wrote a proportion: F1 original force, F2 the final force, so 300 over 60, which is 5 times. So we'll need 5 times less force if we apply 96 centimeter tube. Looking at pressure. So first things first, we need to define pressure. Definition of pressure is simply P is equal to force over area, and unit of pressure is 1 Pascal, which is equal to 1 Newton over 1 meter squared. Second part of this question is pressure a vector or scalar quantity? Now, pressure is a scalar. The reason being is that in any volume, pressure will act in all directions. So it will act up, down, left, right, and so on. So because it's acting in all directions, we cannot pick any preferential direction at which the pressure would act, and hence pressure is a scalar. Vectored quantities, on the other hand, are quantities where there is a clear and definite direction. For instance, this is a vector quantity, and pressure is not that. Pressure is a scalar. The next question is state Boyle's law. So Boyle's law stated simply that pressure for constant amount of gas and at constant temperature that pressure is inversely proportional to the volume of a gas, or we can restate it in a similar fashion as P multiplied by V is equal to a constant value. A constant value of some sorts. It's important that we state that it's at constant amount of gas and at constant temperature in answering questions about Boyle's law. So the next part of this question is asking us to calculate pressure in a column of liquid. We know that that pressure, it's the part of with the Seawolf submarine. So we know that that pressure in a column of liquid, P is equal to rho, which is the density times acceleration due to gravity times the height of that column of liquid. Now, in this case, we don't have any mention of the atmospheric pressure P0, so we don't need to concern ourselves with it in the equation. Sometimes you might notice that atmospheric pressure will be listed in the question, so then pressure of the column of liquid will include that term plus atmospheric pressure. But in this case, we have absolutely zero mention of atmospheric pressure, so we can completely forget about this. So now we know what density is in this case. That's 1000 kilograms per meters cubed. We know what acceleration due to gravity is, 9.8, and we're looking for height. And also pressure in this case is 7154 times 10 to 7. I'll just rewrite it again. Bear with me for a second. So from this we can find height, which is equal to 7.154 times 10 to the power of 6 divided by 1000 times 10 times 9.8, and that value is equal to 730 meters. I did this calculation including the atmospheric pressure, and with atmospheric pressure taken into consideration, that value would be equal to 719. But in this case, this is our final answer, so let me just get rid of this and get rid of this. Okay, so that's that. Looking at question with a little bit more difficulty, the one in the yellow field. So we have to state the Archimedes principle, and Archimedes principle is very simply the upthrust force is equal to the weight of displaced fluid. That's the statement of the Archimedes principle. Now we're looking at a fairly specific case where we're looking at a weather balloon with some volume V that's experiencing an upthrust force. Let's mark it as U, and we also know that that balloon will have some weight. Let's call that weight W. So the upthrust force is the same as the weight of displaced fluid. Displaced fluid in this case is air, and the weight of the displaced air will be mass of that air times acceleration due to gravity. Now mass of that air is the mass displaced by that volume, so we can find it by multiplying the density of air times the volume of the balloon times the acceleration of the gravity. So now we know that upthrust will be equal to 1.25 for the density times 25 for the volume times 9.8. So the upthrust force is 306 newtons. Second part of the question is we have to calculate the total weight of the inflated balloon. So weight of the balloon is mass of the balloon times acceleration due to gravity. I'll read this actually, let me rewrite it. Mass times gravity. Now mass is mass of the balloon itself plus mass of the gas. Now we know what the mass of the balloon is. We know that it's 10 kilograms, so we need to find the mass of the gas inside in the balloon, the mass of the hydrogen in it. So to find that, we need to multiply the volume of the gas in the balloon by the density of that gas. So now we get that total mass of the balloon is equal to 10 kilograms plus 0.12 for the density of hydrogen times 25 meters cubed, which is equal to 13 kilograms total. So that's the total mass of the balloon. So now we can calculate the weight of the balloon, which will be equal to 13 kilograms times 9.8, which will be equal to 127.4 newtons. So that's the weight of the balloon. Now, what is the maximum load that this balloon can carry? The maximum load that this balloon can carry will be in case where the upthrust force is equal to the total weight of balloon and load. So that force acting downwards will be equal to forces from the weight of the balloon and weight of the load. And the maximum load can happen where the sum of those two forces is equal to the upthrust. And that comes from Newton's first law. So if those two forces are equal in balance, this balloon can move up at constant speed. So now we're looking for the weight of the load. To find the weight of the load, we need to subtract weight of the balloon from the upthrust. We calculated those two values earlier, so substitute 306 minus 127.4, we get the weight of the load of 178.6 newtons. Now we know that weight of the load is mass of the load times gravity, so mass of the load is weight divided by gravity, which is 178.6 by 9.8, and that's 18.22 kilograms. If you have any questions about any of those solutions, please note them and let me know. I hope this was useful, and thank you very much.